pleasure also to present Jordi Cirera. Most of you already know him. He's a Ramon y Cajal researcher in the Department of Inorganic Chemistry, Inorganic and Organic Chemistry. He did the PhD here also at the UB with Eliseo Ruiz and Santiago Alvarez. Then he moved to the United States with Professor Solomon at Stanford University and also with Professor Francesco Paisani at Universidad de California, San Diego. And then he came back with a Beatriz Pinos Fellowship first and then a Ramon y Cajal. He is very interested in spin crossover compounds and he's gonna explain us a bit more about that topic. And the talk title, Exploring the Ligand Chemical Space in Spin Crossover Molecules with Electronic Structure Methods. So thank you, and the floor is yours.
Thank you very much, Silvia. So thank you, everybody, for coming after the coffee break to listen to my presentation. Truth to be told, I wasn't the first option for this presentation. There was supposed to be somebody else here, and not I was the second option. But in any case, okay, I hope that I can entertain you for the next 20-25 minutes and live up to the expectation. So indeed, I'm going to show you how we use electronic structure methods to model spin crossover systems. In particularly today, we will focus only on molecular species, although we do some calculations also in condensed phase. But for the topic today, I will focus only on molecular systems. Now, to introduce the subject, okay, indeed, we work in the inorganic chemistry department, so we have like all these inorganic molecular orbital mess up ideas in the head. And one of the things that we learn in our advanced inorganic chemistry courses is that if you have a metal center surrounded by anions or ligands or any coordination environment, the d orbitals are going to split into different subsets. Mostly you're going to have a set of non-bonding orbitals and a set of anti-bonding orbitals. This is the textbook case for the octahedral case with 6 sigma donor ligands. But that's going to happen for any coordination environment, and depending on the nature of your orbitals, you're going to have a larger or smaller splitting. Now, for the particular case here, if we use this as an example, if you use strong ligands such as cyanides or carbonyls, the splitting becomes very large, and then you have a very large gap. And to avoid the energy cost of placing electrons in these antibonding orbitals, you usually pair the electrons in the set of non-bonding orbitals. The opposite case is when you have weak ligands, such as water, chlorine, stuff like that, okay, in which the splitting is very small. And to avoid the interelectronic repulsion, you usually occupy the antibonding orbitals. But in some cases, you can generate a splitting such as both cases are more or less, both penalties are similar. And in those cases, you have 2 electronic states that are very close in energy, and it's possible to switch from one spin state to the other spin state using an external perturbation. Most commonly, this external perturbation is going to be the temperature, but you can induce the transition also applying pressure, or you can modulate the transition by, say, applying pressure or electromagnetic radiation. Okay. This transition, like any other process in chemistry, is going to be controlled by the corresponding change in the free energy, which has an enthalpy term and an entropic term. The enthalpic term is essentially the difference of energy between these 2 electronic states, between these 2 minima, with a small vibrational correction. Okay. And that's going to be positive. And so it's going to be positive, the change in the entropy, okay? Because when we move from the low spin state to the high spin state, we populate antibonding orbitals. But in any case, it's going to be positive. So both terms are positive, but we have a minus sign here, meaning that if we raise the temperature at some point, delta H is going to be equals to T delta S. Both terms are going to be the same magnitude. Delta G is going to vanish, which means that the equilibrium constant is equals to 1. Okay, and then we have the same population of both spin states. That particular temperature is known as the transition temperature, and that's going to be mostly what we are going to be focusing today on how to calculate this magnitude. Also the spin state energy gap, the delta H, but mostly the transition temperature. Now, as you can see here, for the case of having 6 electrons, which is iron 2, which is the most common case, the change with the change on the spin state produces profound changes in the physical properties of your molecule. You go from a diamagnetic molecule to a paramagnetic system. You have changes in the coordination environment because you are populating antibonding orbitals, which means that your bond lengths are going to be larger. There are changes in the absorption spectra because you change the spectral term. So there are many changes that you can measure associated with the change in the spin state, which is good because this switching behavior, the fact that you can use these molecules as molecular switches, can be harnessed to build devices. Okay, and indeed, many people have been working in that field, and they have been using these molecules in some sort of molecular structures in which you can do many things just using all the tools that chemistry puts at hand. Okay, for instance, you have these molecules here in which you can activate or deactivate the spin crossover behavior by photoisomerizating these ligands. You can build small clusters with more than one metal center that have a stepwise transition, and they can be used as logical gates. Okay, if you are thinking about quantum computing, there are porous materials in which the metal center is an iron metal center that can undergo a spin transition that are sensitive to the nature of the gas molecule that you place in the pores, which means that you can use them as sensors, and they can be used also as spin filters in molecular junctions, because you can allow or suppress the flow of electrons depending on the spin state of the metal center, which is kind of cool, because that means that when I have to write grants, okay, I can always tell people that I am working on another technology or now applications on devices, but this is fundamentally an electronic structure problem, okay? So as we said before, we have two electronic states that are close in energy, and if we want to compute the transition temperature, or if we want to compute the delta H and the delta S, we have to, first of all, rewrite this expression here. In the enthalpy term, we have the electronic state and a small vibrational contribution. The entropic term has a small contribution that comes from the degeneracy of the ground state, but it's mostly the vibrations of the molecule. But in any case, you can rearrange these expressions and explicitly write down here the spin state energy gap, this quantity here. Now, in order to get accurate delta G's, you need to get accurate spin state energy gaps. Okay, and that's going to be the main problem when you try to compute thermochemistry in spin crossover systems. You can choose whatever method you want, okay, but this is not a problem that is going to be just solved by going to higher levels of theory. You can use CASPT2 or NetPT2, or you can use two multi-configurational methods, Capet cluster, and so on. Still, for some cases, it's not going to work. Okay, so this is a problem that is difficult because those quantities depend on the occupation of the orbitals. There's a lot of exchange correlation issues and so on and so forth. But in any case, okay, you need to get this quantity as accurate as possible. Okay, meaning that well, you have to calibrate yourself and see what works and what doesn't work. Okay, as I say here, there is not a unique answer to this problem. You can go to wave function methods, or you can stick to density functional methods, as we did, because we thought that it would be interesting to be able to screen different molecules, different ligands, chemical modifications. So we need to go to something that was relatively accurate yet cheap in terms of computational cost. Okay. What's the problem? That there is a lot of exchange correlation functionals to choose from. So the first thing that you have to do is to scan, search, and locate something that actually gives you accurate values for this quantity. Okay. In order to do so, people usually go to the libraries, to the G3/99 data set or stuff like that, and get atomization energies and these things, and then you calibrate your functionals against those quantities. In our case, because we are interested in the thermochemistry, we had to assemble our own data set of spin crossover molecules. Okay, this is the original data set that we use for the original publication, although right now we have around 30 systems in this data set, and all those molecules cover from D4 to D7 metal ions, chromium, manganese, manganese 2, manganese 3, iron 3, iron 2, and cobalt 2, all the metals from the first row that experience a spin crossover. All those molecules have the thermochemistry measured from the experimental point of view. They have sharp transitions. As long as possible, we try to get neutral molecules to avoid problems with counter ions. So we try to build a data set in which the experimental data was reliable to calibrate against the molecule. Not always is possible. Some of those molecules have a net positive charge, so you can see here, but that's the best that we get. Okay, and with all those systems, we benchmark different density functional methods. I mean, this is a problem that people has been working for many years. So we already knew that there was some exchange correlation functionals that perform more or less okay for specific systems, for iron 2, for iron 3. Okay, there was some data out there, but we decided to go systematic, and for each one of those molecules, we fully optimize the molecule in the low spin state, fully optimize the molecule in the high spin state, calculate the spin state energy gap, and plot it against the amount of exchange correlation or Hartree-Fock exchange that you have in your functional, okay, which is summarizing here. Each one of those functionals, those are the functionals that we tested, those are the 20 molecules. Each one of the functionals has 20 bars, although some of them overlap, okay? And this is the amount of Hartree-Fock that you have in your functional. Obviously, the more Hartree-Fock that you mix, the more you stabilize the high spin state to the point that the almighty powerful B3 leap doesn't work very well for this particular problem. Okay, but as you can see, there is only one functional, which is the hybrid version of the TPSS functional, which has a 10% of Hartree-Fock exchange that actually give us the right position of the low spin state being below the high spin state for all systems. But as I always say, even though this functional performs okay for this problem, and it seems to be the logical method of choice or the best method of choice if you have no idea of if your system undergoes a spin transition or if you're doing some virtual screening or stuff like that. There are other functionals that can be used as well. For instance, OPBE performs more or less okay for some of the systems. It fails for some other systems. And the B3 star, which is a functional that was developed specifically to reproduce a spin crossover in iron systems, it performs very well for iron, but for some of the cobalt, manganese systems and the chromium system, it fails. Okay, so what do I want to say with that? That in general, TPSSH with a triple zeta basis set with prioritizations seems a reasonable method of choice for the calculation of spin state energy gaps, but some particular cases or some particular problems may be better if you want to be more quantitative towards a specific system. OPBE or B3 star, they may very well outperform TPSSH. But in general, it seems that it provides like with a reasonable window of energies, okay? And moreover, the important thing is that here in green, you have the usual experimental range of the enthalpy change in spin crossover systems, which goes in between 2 and 8 kcal per mole, okay, which is this green range here. So TPSSH, essentially, for most of the cases, in some cases, it overshoots the energy, so that's OPB, but in most of the cases, falls within this range, meaning that it's giving us a more or less good description of the relative position of the two spin states. If that is the case, okay, so if our spin states energies are accurate enough, we can correct them with the harmonic frequencies, okay, get the thermal dependence of the thermochemical quantities, okay, and then we can get plots like this in which you have the change in the delta G, that when it vanishes, it means that the enthalpy and the T delta S are the same, and actually extract transition temperatures. Okay, so this is how we do it at the end of the day. We can use some of those expressions or other ways, but essentially, is it possible to extract transition temperatures? Okay, and it can be modeled to some extent with a certain degree of accuracy. Okay, so we've been doing this for a while. Okay, and I'll show you some specific cases and how we translate all the information that we get from the electronic structure point of view, all these molecular orbital pictures and the understanding that we get into simple expressions that actually allows us to connect with the experimental counterpart. Okay, so this is a very interesting case because we have an iron 2 molecule that is tetracoordinated. So if you remember your inorganic chemistry, advanced inorganic chemistry courses, they always tell you that tetracoordinated compounds should be high spin because the splitting is too small and they are always high spin systems. But this particular molecule undergoes transition. Okay, and not only that, there is a dependency of the transition temperature with the size of this phosphine. Okay, so if you use bulkier phosphines, you have a very high transition temperature. If you use small phosphines, the transition temperature goes down by 100 and by almost 40 kelvins. Okay, and there seems to be a correlation between the size of the Tolman-Kohn angle, which measures the volume of this phosphine, and the transition temperature. So the experimentalist told us, can you take a look, can you analyze what's going on here and explain why this molecule undergoes a spin transition and why there is this correlation with the Tolman-Kohn angle? So we did. We took a look at the electronic structure. And the first thing that we've noticed is that the combination of this umbrella distortion imposed by the tridentate ligand with the negative charge of the nitrogen actually splits the orbital in the reverse pattern. Okay, so you will expect to have 3 over 2 orbitals as in the tetrahedral case, but the umbrella distortion and the negative charge pulls one of the orbitals down in energy, and you end up having the octahedral case 3 plus 2 orbitals. So this is a coordination compound that from the coordination number point of view is a tetracoordinated molecule, but from the electronic structure point of view, it behaves like an octahedral compound. So you have essentially 3 mostly non-bonding orbitals and 2 antibonding orbitals that are antibonding with the carbons here. You can see that this carbon-iron bond, even though you can probably see, you can see the green lobes here, they are antibonding. Probably you can see it better here with the d orbital. Okay, you also have the negative charge of the nitrogen, okay, a pi orbital that is antibonding with the d orbital. So those 2 orbitals are strongly antibonding, and these 3 orbitals are essentially non-bonding. Okay, so we computed the transition temperatures for the ones that are available experimentally. Okay, those in black you have the computed values, and in red the experimental values. So in some cases we are off, but in some cases we are very close to the actual value. We even calculated some molecules that are not in the original data set to see if the correlation with the Tolman-Kohn angle actually follows up. So we were able to fill in some experimental gaps. Okay, and this is the correlation for the experimental data. Okay, there's a decrease with the Tolman-Kohn angle. This is our computed values. Okay, we can also reproduce the decrease in the transition temperature associated with the size in the in the phosphine con angle, okay? And the explanation for that, okay, so the actual explanation that you can get taking a look at the molecular orbitals is that if you have a very bulky phosphine, such as triphenyl phosphine, this part here is very bulky, okay? And then you have a steric congestion with these mesyl groups, meaning that this anionic ligand cannot go all the way into the cavity. Somehow it gets stuck outside. But because it has a negative charge, it picks up the iron and pulls it off. It enlarges this carbon-iron bond, okay, and reduces the antibonding character of these orbitals, okay? By reducing the antibonding character of these orbitals go down in energy, you require less energy for undergoing the transition, and that means smaller transition temperatures. On the other hand, if you have a very small phosphine, such as PH3 or 3-methylphosphine, this ligand can go all the way into the cavity. You maximize the antibonding interaction between the carbon and the iron. These d orbitals become more and more antibonding. They go up in energy. The gap becomes larger, and you require more energy to undergo the transition. Okay, and that's the explanation that we give the experimentalist. Okay, and they didn't care at all. Okay, the only thing that they care was this thing here. Okay, because this is cool for theoretical people for computational chemistry, and it's very cool, and you have your orbitals. But what they were fascinating were with the fact that we can build simple correlations that actually summarize all this data in a very simple expression. Okay, so in this correlation, we have indeed the correlation with the Tolman-Kohn angle, but the explanation for this linear relationship is based on the electronic structure. Okay, so we are getting more or less right numbers. I think that the accuracy is more than enough for this type of calculations. We are getting a proper explanation on the basis of the underlying electronic structure, and we can summarize all of this into a simple expression that for the experimentalist is very handy, because it means that they can just select a given phosphine and more or less know where the transition temperature is going to be. Okay, with that idea in mind, and knowing that the functional is able to more or less quantitatively compute transition temperatures, we've been doing more recently exploration of ligands that for some reason are difficult to work in the lab, either because they are air sensitive, either because there are very few examples of the systems, or because they are interesting because instead of iron 2, they use iron 3, which is stable to oxidation, and they generate other families of spin crossover compounds that are more interesting. Okay, so more recently, what we've been doing is not just trying to reproduce the experimental information, but just trying to explore how we can modify some of the ligands or some of the data that is out there that is incomplete in order to study how we can functionalize the molecules so we can move the transition temperature up or down, which is what I'm going to show you for the rest of the talk. Okay. Now, the first compound that I want to talk about is this molecule. This is an anionic spin crossover molecule. There are very few examples of anionic spin crossover systems. Okay, there are very few, actually. But it turns out that they are interesting because they can be inserted in multifunctional fluorescence materials. So they have some technological applications that makes them relevant. Okay, and we thought, okay, if this is interesting, and because there are very few examples, let's get one and let's analyze how we can tune the transition temperature by playing around with the different positions of the ligands in which we can apply chemical modifications. Okay, so this is the original molecule extracted from the database. And here is a sketch of the molecule. You have an iron 2 compound, a net negative charge, okay? And there are more positions, okay? But we choose 3 different positions in which we can play around. This position here, the length of the aliphatic chain, the para position of the aromatic rings, which is R2, and obviously these thiocyanate ligands that can be replaced by serenocyanates or isocyanates or whatever. So there is like plenty of things that you can modify in this molecule in order to see how the transition temperature change. Okay, so the first thing that we analyzed was the length of that change here. Okay, you can in principle make it put alkoxide or alkane groups, and you can make it as large as you want. Okay, we made it grow up to 4 CH2 groups. Okay, but in principle, you can see from this graphic that except from plugging an OH or a C in this position, okay, which makes some difference, enlarging this chain doesn't make any difference. Your transition temperature essentially becomes constant. Okay, that brings up to an important point. Okay, so the fact that this length is not affecting the electronic structure of the iron metal center, which somehow is expected because this is far away from the coordination environment, doesn't mean that it cannot have an important effect in modulating the shape in the actual crystal. Because if you have long chains here, there could be van der Waals interactions in the crystal that ultimately tweak or tune a little bit the overall behavior. Okay, here we are analyzing only the molecule and the electronic structure of the system. There can be crystal packing effects that we are not accounting for that ultimately can modulate the overall transition. Okay, but that can be done with other techniques. But in principle, it doesn't seem that you can play too much with the transition temperature just by enlarging this change here, which again, it's sort of expected. Okay, There's a complete different picture if you change the L2 ligands. Okay, so if you use ligands that are increasing in ligand field, isocyanate, thiocyanate, selenosyanate, and NCBH3, okay, you can raise your transition temperature from 50 kelvins to 400 kelvins. So basically, you can move one order of magnitude from 50 to 500 kelvins just by replacing the ligands around the iron metal center. This can be understood on terms of the electronic structure of the metal. You can see how this pi antibonding interaction, it gets smaller and smaller to the point that it gets reversed here with the NCBH3. It all is related with the size of the pi orbital of the oxygen, sulfur, selenium, or the fact that you don't have a pi orbital here. Okay, so it can be rationalized in terms of the molecular orbital picture. But if you plot your computed transition temperature against this F factor, which measures the strength of those ligands in sort of a spectrochemical series, you get this linear correlation, okay, which again, you can plot it as a function of the splitting of the non-bonding and antibonding orbitals, which is also in here, okay? So there is a drastic effect. Okay? You can go from basically a high spin system to a low spin system, and you can play around a little bit, okay? But those changes are very abrupt, okay? So you move in blocks of 100 kelvins up to 400 kelvin. So there is like a huge jump from here to here and from here to here. Okay, so is it possible to get systems in this region here and in this region here? Okay, well, you can if you play at the same time with these axial ligands and with the para position of the phenyl rings. Okay, so what we did was functionalize this R2 position with electrodonor or electroattractor groups. Okay, you have here some of the substituents that we put in this R2 position, and we compute the transition temperature for this molecule with thiocyanates, selenocyanates, or NCBH3, okay, which are these three lines here. Obviously, the correlation is not perfect, okay, so we are just looking at tendencies. But one more time, we can write these expressions in which we have the computed value of the transition temperature as a function of the sigma para Hammett parameter. Okay, you can see that the slopes are very similar for the NCBH3 and for the selenocyanate. Okay, it's a little bit steeper for the thiocyanate, but still the trend is the same, meaning that once you are located in the 100s, 200s, or 400s kelvins, with the electroattractor or electrodonor groups, you can tune up or tune down the transition temperature by a little bit. So you have two knots to play, okay, and there is a high degree of tunability in the transition temperature in that system if you are able to play with these two quantities. Okay, so you can locate you can use, for instance, selenosyanate and lock yourself around 200, and then you can tune down by 20 or 25 kelvins or 30 kelvins up just by playing with these R2 positions. Okay, so there are two ways to tune the transition temperature. Now the analysis, okay, this analysis can be extended and it's general. Okay, so having electrodonor or electroattractor groups, it always produces the same time of tendencies. The same, you have a positive lobe here, and it happens the same for these molecules. Here we have iron 3 complexes, which are more interesting than the iron 2 complexes because they do not oxidize. The problem with the iron 2 spin crossover molecules is that over the time they oxidize to iron 3 and they lose the spin crossover behavior. So the spin crossover community is very interested in making spin crossover compounds with iron 3, but there are way many less examples than for iron 2. Okay, so we decided to do the same thing, to functionalize here the positions, a little bit the same idea. Okay, for this molecule, obviously the correlation with the Swain-Lupton or with the sigma, with the Hammett parameters is the same. Okay, so you have an increasing trend in the transition temperature when you put electrodonor groups and you lower the transition temperature down with electroattractor groups, okay, and you can write this expression. The effect here is much larger because you are functionalizing directly the ligand here. Here, you are functionalizing these phenyl groups, which are farther away from the iron, so the effect is much more subtle, okay? So there's nothing new here, but in that particular case, for the particular systems, okay, we've analyzed if there was something else in there that we can scratch, because the idea is that we are generating a bunch of data, so we are getting a lot of electronic structure data of orbitals and stuff. So at some point we are interested in systematizing this in some sort of machine learning algorithm if we can extract or analyze all this data in a reasonable way. Okay, so analyzing this system, what we find out is that actually the partial charge of the nitrogen can be directly correlated with the transition temperature. Okay, and it happens for both spin states. Okay, which means that I don't have to optimize the low spin state, I don't have to optimize the high spin state, I don't have to calculate the spin state energy gap and do everything that I did. I just need to calculate one of the two spin states. Right? I can do the high spin or the low spin state, and just by getting the energy of the partial charge of the nitrogen on each spin state, I can make an estimation of the enthalpy change or the transition temperature, okay, which actually speeds up a lot the computational cost of studying those systems, because if I only have to calculate one of the two spin states, that's much faster, okay? And as I said, okay, up to here, we've always been able to correlate this with a single parameter, okay? But in some cases, it's a little bit more complicated than that. I mean, usually we try to narrow down all the electronic structure picture to a very simple correlation, but in some other cases, it's a little bit more difficult, okay? This is the last case I'm going to show. Okay, this is the chromium indenyl compound. This is a chromium 2 spin crossover system. There are, again, very few compounds with chromium that undergo spin crossover behavior, which again makes them interesting. Okay, it's hard to work with these molecules. They are air sensitive, water sensitive, everything sensitive. Okay, so you have to work in the glove box. Making measurements is difficult. Okay, so it's always handy if the computational people can actually understand the behavior and make some predictions. Okay, so you can actually go with a little bit more of information before starting doing synthesis and finding out that nothing worked. Okay, there is a little bit more of complexity than just analyzing the molecule, because the molecule can be in the eclipsed or staggered configuration, and that has some implications on the delta S, but I'm not going to explain this in detail. Okay, but what is observed experimentally is that if you start placing methyl groups in this ligand, if you put more than one methyl up to the fully methylated system, you are making the ligand field around the chromium center larger, because you go from a high spin system to a low spin system, meaning that here the spin state energy is very little and here is very large. Okay, so we are tweaking this energy gap just by placing methyl groups into the indenyl ligand. Okay, that's somehow expected. Okay, and that happens also for the manganosine compounds. It's exactly the same idea, but here there has to be something else, because we are putting one methyl group here and one methyl group here, so we are only adding one methyl group, yet we go from a high spin system to a spin crossover system. And the same here, we have 3 methyl groups and 3 methyl groups, yet the experimental transition temperatures are completely different. So it's not just a matter of adding methyl groups. It seems that it's more important where are we placing those methyl groups than the actual number of methyl groups that we are putting in the ligand. Okay, so we decided to analyze this in a fully systematic way. So we calculated all the molecules with one possibility of having one methyl group, 2, 3, 4. We did all the calculations. Okay, and then we analyzed the data. Okay, so we built a small, we analyzed the data with a small program. Okay, and we try to find out how many types of carbons we have in our system. Okay, and actually we detected that the minimum number of different carbon centers that we need to reproduce the density functional theory data is 3 types of carbons. We have the carbon A, which there is only one type in this position, carbon B, which are those carbons B here, and carbon C here. Okay, and the ratio, the different weight between these positions is that placing a methyl group here in the A position or placing a methyl group in the C position, has a 6-time fold effect with respect to putting in the 1 position. Or if you put it in the B position, you have a twice as large effect than if you put it in the A position. Okay, so those are the different weights, but if you analyze, that's the ratio that you have. What does that mean? Okay, it means that if we have 2 methyl groups and we put the 2 methyl groups here, we are having a 12-fold effect respect of having a methyl group, for instance, in the B position and the A position. So those 2 positions, for whatever the reason it is, because I've never got like a clear picture of why this is happening, they seem to have a much larger effect on the spin state energy gap. Okay, the usual way that people do this is just by counting the number of methyl groups. Here you have a ligand with 3 methyl groups and you have a ligand with 3 methyl groups, but if you use these coefficients, you can see that actually the impact of placing the methyl groups here is 13, which is a much larger value than if you put it here. Okay, with the coefficients. If you use this weighted coefficient or weighted methyl group, okay, you can see that you can reproduce very well the TPSSH data, the spin state energy gaps. Okay, so this linear expression with those relative weights can actually reproduce the experimental data to the point that it allows us to make predictions. Okay, so we obviously correlated the data with experimental values and with our own data, but we also generated a ligand that wasn't in the original data set. We decided to put the methyl groups here to see what happened. Okay, and the value that the model predicts is 0.71, and the actual calculation, if you do the density functional calculation, optimization of the high spin state, low spin state, and everything, is 0.9. Okay, so the model actually predicts very well this spin state energy gap, again telling you that if you want to get a very large splitting, the places in which you should target your functionalization are the C positions, and if you want to play in a more subtle way, you should either go for the B positions or for the A position. Okay. Obviously, all of this can be understood in terms of the electronic structure of the system. You can go to the molecular orbitals, you can analyze, you can understand why this is happening. But over the years, I figured out that this is interesting for a certain part of the inorganic chemistry community. But again, the experimentalists, they think that those are cool and they provide with information, but they are much happier with the expression that allows you to get directly to the transition temperature. Okay. Okay. And with that, I arrived to the end. Okay, so overall, I think that the main message that we can take from here is that even though calculation of spin state energy gaps is a challenging problem for computational chemistry, doesn't matter which method you choose. Okay, is it possible, at least with density functional theory and with particularly DPSSH, but also with some other functionals, get accurate values for this quantity that can in turn be corrected to extract transition temperatures? More importantly, that we can explain the experimental trends, okay, on the terms of the electronic structure of the system, which in turn allows us to make some predictions or to fill in some gaps in a series of molecular systems. And obviously, as I told you, even though I didn't show here, all of this can be extended to condensed phase to account for crystal packing effects. Okay, in our experience, because it's a typical question, no? I mean, but what happens when you do the crystal? I mean, the answer, the truth is that it depends on the system, but in some cases, the crystal packing effects do not interfere too much, or they produce similar results if you do the calculation in crystal as if you do it in the molecular system. Okay, but more importantly, okay, we have a method that reproduces experimental data and can make some predictions. So I think that this should be used to actually explore, okay, things that from the experimental point of view are complex, either because you are using metals or ligands that are hard to work in the lab, because there are very few examples, because there are little literature on a particular subject. Okay, so we can use these computational tools to expand the data set on spin crossover molecules and actually help the experimentalist counterpart to locate themselves in a specific region. Okay, we can make a rational design of ligands that can tune the transition temperature. Okay, and in turn, if we can do all of this, we can accelerate the design of new spin crossover molecules with telluric properties. Okay, and with that, I have to acknowledge the funding, IQTC, Maria de Maetu. Without the funding, it would be impossible. I show you mostly the work of Laia Navarro and Daniel Vidal. Okay, and obviously all of you for your kind attention. Thank you very much.
Thank you very much for the time, Jordi. Question time?
Maybe it's an ignorant question, but I would have expected relativistic effects or spin orbit coupling to be quite important,
yeah,
in these systems, because if you had no spin orbit coupling, you wouldn't see the other species at all.
We checked that. Okay, so in this original work, we actually applied every correction that we could, the solvent, relativistic, and so on. Okay, so it's true that there is some correction, okay, that but at the end of the day, it doesn't pay off to do it. I mean, it's minimal, okay, and it's always in the same direction. Okay, so you can add it if you want, or you can use relativistic. We don't do calculations with the relativistic pseudo potentials, but if you, I think that we did with the DKH method. Okay, I don't remember, but I think that it's DKH. We can check it on the later on if you are interested, but the correction is it's little compared with the total spin state energy gap. So it doesn't.
Not even in the crossing region.
Could be, but I mean, in terms of because what we do is optimize the molecule. No, we didn't scan the whole potential energy surface. So we only calculate one minimum and the other minimum. Okay, so actually, if you are, what you're saying is correct. If you are scanning through the potential energy surface at the crossing point, yes, but we don't do that. We just get the energy of one local minimum and the energy of the other local minimum. And with those 2 points, then we compute all the quantities.
Thanks for your talk. Very, very interesting. So that's clear that computing energy differences between different spin states is challenging, but it's becoming more and more important in chemistry, because now there is the explosion of radical chemistry in catalysis, photocatalysis, and you have very, very nice results. So you know that. So you convinced me about the suitability of TPSSH as a religion. Since this time, I have been using TPSSH for computing any difference when spin states are involved. but I have some doubts in my religion. So, and
That's normal. That's normal.
so, but the doubt is related with the this low cost, highly correlated methods, the DLPNO and similar methods that more and more are becoming methods for benchmarking in closed shell systems. So the question is, you have a very nice database. So someone has taken to apply this kind of methods. I think that there were some criticism about the old versions, but they have presented more advanced versions of the DLPNO that they claim to be useful for this kind of problems. Does anyone have checked this database for computing with this kind of methods?
Short answer, no. But okay, so there's people that has been doing the DLPNO method for the typical iron with 6 ammonia and things like that. So they do the classic benchmarking with these molecules that are simplistic for the same reason. But now I don't have the answer yet, but we are working with our idea. When I sent Laia over John's lab in Oxford, was to actually at the end of the work that she's doing over there, be able to compute all this data set with one of those advanced methods that uses a CAS-SCF calculation, CAS-PDU calculation corrected with a DFT. Okay, so at the end of the day, the answer is maybe I do it myself at some point, and I'll try to do it. With Eliseo, we've thought about doing this with but it didn't work. At least the calculations that we started doing, they weren't producing as good as results as we were expecting.
With coupled cluster, you always overestimate the stability of the high spin state, and basically all the Hartree Fock methods, you have exactly the same problem. Even if you go to a very large CAS-SCF active space, you have the same problem. The only thing that you can save a little bit of computer time is with R2 scan functional, is meta-GGA, is not hybrid. The results are more or less similar than those that you obtain with TP-SSH.
The energies are slightly larger, but yeah, but it's similar. The best you can do. Yeah.
No, this kind of DLPNO methods, I am not talking about CAS-SCF, but this kind of very time-consuming methods. These kind of methods are very appealing because they are extremely fast. And I don't know if they can be so cheap and so good. Okay, but I think that more and more the referees are asking, can you check, can you calibrate the results with this kind of methods?
This is something that we always had on the to-do list, but we never did. Okay.
You have exactly the same problem that I mentioned. You overestimate the stability of the high spin. Then you have two large energy differences. Coupled cluster or the DPLN method that you have in Orca is exactly the same.
Thank you very much. I have a question on a different direction. So these spin crossover systems have been very much interesting also when you go to extended systems, especially for collective effects, whether you have hysteresis in your phase transition exactly. Now, my question is, which is the situation right now in this extended world of spin crossover? Because this is, I remember a couple of years ago, everybody was looking into these extended states and these calculations are heavy.
Yeah.
So how do you attack that?
Exactly. So there are two schools. Okay. So there is the school of making a model of your exactly, and that's one option. Okay. That's one option. Okay. So the other option involves a completely different approximation. Okay, so I don't have the slides here, but I can show you later on if you are interested. Okay, so there is another option, which is there is the possibility of generating force fields that actually account for the relative position of the two spin states energy gaps. Okay, so then you can run, those are specific force fields that you have to develop for the iron because they are not, you have to parameterize. Usually you calibrate your parameters against the TP-SSH. Okay, so we've done that. Okay, once you have these force fields that properly reproduce the position of the two energy states, then you can run simulations in which you can warm up a large chunk of your system and couple it with a Monte Carlo algorithm. Okay, meaning that at each step of your simulation, you can calculate the difference of energy between the high spin and the low spin for each metal center. And either flip the spin or keep the spin in its previous position, okay, across your simulation. You can do this multiple times back and forth, okay, and then you can model the transition curve for a extended chunk, okay? And we've done that, okay, although it's very hard. Not the calculations are not expensive. What it's hard is to generate the force fields. That's super expensive in terms of human cost, not in calculation, but it takes time and it's tedious, okay? But we've done that, and this methodology is able to reproduce the experimental data, and it's also able to reproduce the effect of having different gas molecules in the pores, okay? So, but it's a completely different approach, okay? It's a more statistical mechanics approach, okay? Okay, so that's how I will do it for condensed phase, okay? For the second question, which is the hysteresis and so on, okay, that's largely dependent on the size of the system, okay? So if you want to reproduce the hysteresis, you really need a large chunk, okay? We did it with a 700 atom, more or less, and it wasn't enough to reproduce the hysteresis. So in order to get some differences between warming up and cooling down, we need to put at least 2000 atoms in the simulation, okay, which is a lot, because then you start having the domains and everything. The problem with with a relatively small piece is that the moment that one of your metals expand, it triggers like a wave effect around. If the system is large enough, then you can start having pockets, and then you can see differences actually. Okay.
Thanks, Jordi. Can you comment a little bit more on your ideas about using the NBO charge? So the assumption must be then that the charge is independent of the spin state.
Yeah.
And is that true?
I will say no, but the thing is that this is the very first case in which I could find this correlation. Okay, so I wasn't able to find this correlation for any other system. So this particular family of iron 3 complexes is the only case in which I found a correlation between the NBO charges. If you use another charges, this correlation disappears. So it might be just a serendipity of that particular case. Okay, and it means that for the iron 3 complexes with those ligands, we can do it, but not for other systems. But for instance, if you go to this family here, okay, and I analyze this, I don't have like such a clear correlation with the carbon NBO charges or with the nitrogen NBO charges. Why? I don't know. Okay, I don't know. But
so is the charge that you show there, is that the low spin or the high spin?
In here you have both. Here is the low spin charge and here is the high spin charge.
Ah, okay.
Low spin charge and the high spin charge. So for that particular case, for iron 3 with those ligands, the correlation appears, okay, with the NBO charges. To which point this is generalizable to all the systems, I don't think that it works. I mean, it may be something of this family, it may be something in the coordination environment, because it's only with the NBO, because we've tested other fitting charge schemes and it doesn't, it correlates, but not as nicely as the NBO.
And does the charge correlate with some structural feature of the molecule? I'm just saying, could you ultimately go to a point where you don't need to do a calculation? You can just identify a feature of the ligand.
Exactly. So this is what we are trying to do. Okay, so it's what I mentioned during my presentation. What we're trying to do is to extract electronic structure parameters, to correlate it with the geometrical coordination environment, typical parameters, you know, bond length, number of donor atoms, type of donor, and see if we can assemble some sort of, call it machine learning or whatever algorithm that actually is able to, just taking a look at the structure, produce the spin state energy gap or the transition temperature. That's the ultimate goal. But what you would like to do is to have a library of ligands and metals and ask, if I put this with this, which will be the transition temperature? Okay, so I think that this is probably the most promising case in which we will be able to generate something such as what you're mentioning. Okay, but again, you have to be careful because I mean, everything depends on everything and it's not trivial, but.
Okay, it has been a nice discussion. So let's thank again Jordi. Okay, so our next speaker is Irene Cuxart. She did the bachelor degree at the UPS in Sarrià and also the master's, and now she's in her 4th year of the PhD doing research in the glycoside hydrolase under the supervision of Carme Rovira. So Irene, all yours.
Thank you very much for having me here and for coming. I'm going to show you my presentation about non-classical mechanisms of glycoside hydrolases. So glycoside hydrolases are a type of enzymes that degrade polysaccharides by degrading the glycosidic bond. The glycosidic bond is a type of bond that unites different sugar units to create a longer sugar chain. glycosyl hydrolases are grouped in 185 families as today. In the KZ database, that it is a database that groups carbohydrate active enzymes depending on sequence homology, and where you can also find all sorts of biochemical information about them. So far in the 20th century, there were two types of mechanisms that were described for glycosyl hydrolases. And for the moment, it was thought that they were the only possible types of mechanisms. In the so-called classical mechanisms, we have two amino acid residues of the enzyme that perform the catalytic action on the substrate. So we have a residue that is the nucleophile and the other one that acts as a general acid base. The two types of classical mechanisms are distinguished according to the anomeric configuration at the anomeric carbon that is adjacent to the bond that is going to be clipped. So we have retaining that maintain the same configuration and inverting mechanisms that invert the configuration. However, in the last years, we found out that there are other possible mechanisms that differ from these ones, also different types of active site architectures. So it is relevant to study these possible alternative mechanisms in order to, for example, fine-tune enzymes or for enzyme engineering purposes, and maybe like explore different activities for the enzymes that we know. On the other hand, conformational preferences of the substrates are a key aspect of enzyme catalysis by glycoside hydrolases. So we know that pyranose rings are really flexible entities that are able to adopt an array of different conformations with their atoms. So some of these conformations are better prepared for enzyme catalysis. So to study like the conformational itineraries, so the different conformations that the substrate adopt along catalysis, is of relevance for the field also to study like how can we design better inhibitors, or how can we design better activity-based probes for our enzymes. So to sum up, the two main questions that we want to answer in glycoside hydrolase catalysis are: what are the reaction mechanisms of our enzymes, and what conformational itineraries undergo our substrates? For that purpose, we use methods based on molecular dynamic simulations. So to start, we need to build our enzyme substrate complex. For that, we take the tridimensional structure of the enzyme, usually available in the protein data bank, or in other cases, if it's an experimental collaboration from the experimentalist collaborators, and then we build the complex. Then we apply classical MD methods to calculate the forces between the atoms of the system. However, we need to take into account that in this step, we will not be able to simulate the reaction because electrons are not properly described, and also sugar ring conformations are not reproduced at this step. For that purpose, we jump to the hybrid QMM methods. In these methods, the chemically active part of our system, so where the reaction is going to take place, we're going to treat them with QM methods, and the rest of the system with MM methods. In this part of the workflow, electron rearrangements can already be observed, and also the sugar ring conformations can be accurately described. However, since we want to describe chemical reactions, so we need to sample from a state of reactants to a state of products that are separated by high energy barriers, we apply enhanced sampling schemes such as metadynamics to efficiently explore the reaction space that we want to simulate. So in this talk, I'm going to talk about two enzymes that follow two non-classical mechanisms. One of them is lactone biosynthase, is an enzyme by a gut bacterium that hydrolyzes human milk saccharides. And the other one is the monocyte phosphorylase, also found in the human gut, that degrades epithelium complex glycans. So we're going to discuss non-classical mechanisms. To recall what we were discussing before, so a classical mechanism is that where like two enzyme residues act on catalysis, and only that. So the substrate doesn't do anything except for like being degraded. But in a non-classical mechanism called like of substrate assistance, in this case by 2N-acetyl substituent, we have the substrate perform the role of the nucleophile of the reaction, while another residue of the enzyme acts as the general acid base. So for this case, it applies to lactone biosynthase. As I said previously, is a bacterial enzyme found especially in infants' gut. It degrades human milk oligosaccharides, and is relevant because these saccharides are really complex structures, difficult to synthesize, and these enzymes could be engineered not for inhibitor design, but rather for try to use their secondary activities, try to make them to synthesize these sugars instead of degrade them. So from structural information, it had already been proposed that this enzyme follows a substrate-assisted mechanism. However, the state of reactants, the Michaelis complex, and the catalytic conformational itinerary was not yet known. For that purpose, we calculated the mechanism. Using the QMM metadynamics workflow I explained before, we were able to simulate the mechanism. So in this movie here, we can see that the 2N-acetyl group of the substrate attacks the anomeric carbon, and this residue acts as general acid base. By studying this mechanism, we also found out that nearby histidine residue present in the active site also assists catalysis by switching its interactions with this residue, that is a polarizing residue for the N-acetyl group, and also interacting with the general acid base as the reaction progresses. So this explains some kinetic data that the crystallographers had with mutants of this residue. So we also found out that the substrate binds to the residue, to the enzyme in a distorted conformation, which facilitates the catalysis. It's the conformational pathway that brings the substrate ready for catalysis. For simulating that, we use two collective variables that represent the two main reactive events that are taking place in this simulation, the nucleophilic substitution and the proton donation. So on the other hand, we studied the monocyte phosphorylase. It is called, it's a bacterium that, an enzyme that it is not yet known what bacterium exactly is the secretor organism. That's why it's called unknown human gut bacterium monocyte phosphorylase. So for this enzyme, it existed structural information, but the crystallographer saw that the residue that was supposed to be the acid base was really far from the oxygen that was in the glycosidic bond, so to its target oxygen to protonate the leaving group. So they suggested that based on structural information, the only possible pathway would be through a double proton transfer from the acid base to a hydroxyl substituent with which it was interacting, and then finally to the oxygen of the leaving group. However, in the crystal structures, we are not able to discern the protons. So it was actually a novel proposal for a mechanism. And so we decided it was an interesting mechanism to study, also because this active site architecture is shared among all the members of the same family of these enzymes. So it is an extended active site architecture. Also, studying this enzyme is relevant for maybe, since this enzyme is related to these IBD diseases, inflammatory bowel disease group of diseases, for inhibitor design as a drug target, and also perhaps for synthesizing high added value products to the reverse reaction, to reverse for phosphorylases. So with QMM metadynamics methods, we were able to simulate the reaction mechanism. Sorry. Excuse me. Yes, now. So here we can see that the acid base donates the proton to the hydroxyl substituent of the substrate, and then this substrate, this proton goes to the leaving group, and then the inorganic phosphate group that acts as a nucleophile. For these, we also used two collective variables that represent the two main reactive events. So with this, we could see that this was another case of substrate-assisted catalysis in which the substrate acts as a catalyst through a double proton relay. Also, but instead of acting the nucleophile, was a hydroxyl group acting as a proton donor. So this mechanism, it was a novel proposal and also can be extended to other family members that share the same non-canonical active site architecture, and also to other enzymes such as the one that's cited here, that is a glycosyl transferase that has been studied recently and shares the same active site architecture. So it is potentially following the same type of mechanism. So to conclude, we were able to describe two enzymes that function through non-classical mechanisms in which the substrate takes an active role in catalysis, either as a nucleophile or either as a proton donor. In the first case, we also found out an additional residue that we didn't expect, but also was assisting in catalysis by switching interactions with the main catalytic residues. And also we found that both substrates underwent complex conformational changes through catalysis that were relevant for it to happen. So to finish, I would really like to acknowledge, thank my group and all of our collaborators on funding and HPC resources. So thank you very much for coming, and questions are welcome.
Thank you very much, Irene, for this nice presentation. Any questions?
Being not in this field, I don't have an idea of these simulations. How long do they take? I mean, when you do this simulation from the beginning to the end, these molecular dynamic simulations, so usually how much computer time do you need for these calculation?
So, okay. So the classical molecular dynamics part is lower in resources and faster. It can just take a few hours of computational time for like maybe one replica of some nanoseconds, considering that maybe in a machine we can have up to more than 100 nanoseconds per day. Then the QMM part and then metadynamics is a bit slower. In QMM, you're in the picosecond scale also. And then, so it depends on the simulation. Some can take, like every step of the calculation is a few seconds long. So depending on how many picoseconds you need to complete the reaction and observe, usually we go for one crossing to one state to the other and then back. So with this, it's more extensive.
Of the, then to get all the pieces. I mean, I'm not in this field. That's why I was interested in seeing how you assemble all the different calculations, because you do various steps. Thank you. Nice work.
Thank you.
Any other questions? Okay, if not, we are going to change to the next speaker. Thank you very much, Irene.
Thank you. Ai, em sembla que us he de tornar això.
Okay, thank you.
Okay, so it's a pleasure to introduce the last speaker of our session. It's Pierre-Francois Loos, and friends. He's a CNRS researcher at the University of Toulouse. He did the PhD at the University of Lorraine, Nancy, under the supervision of Xavier Asfet. Then he moved to Australia, to Australian National University in Canberra, where he was a postdoc for 4 years with Peter Gill, and then he started his own group. He was there for about 5 years, and then he came back to Europe in Toulouse, where he also got a consolidator ERC in 2019. So he's going to tell us a lot about, in this case, selected configuration interaction methods for ground and excited states. So thank you very much, Pierre.
Thank you very much for the kind introduction, and thank you to the organizer for the invitation. We are almost neighbors, so it's always good to meet the neighbors. Yeah, so we're going to shift gears here, I think. So I'm going to talk about more like electronic structure developments, so how create new methods and how do we develop it. So I am in Toulouse. So I'm going to talk about selected CI a little bit. I'm going to explain every single word in the title, I promise. But before, I'd like to introduce our group, what we're doing. I think it's always useful to know what other people are doing if you are interested, and we can talk. so on. So we are mainly focusing on excited states, okay, how to get excited state energies and properties as accurate as possible. If I was at the University of Barcelona, I would probably be more a B guy than a U guy. Our systems are fairly small. Those spin crossover systems are quite huge for me, so it's going to be fairly small. I think I'll go up to benzene, maybe. That's what I do. So we worked on various things. So today I'm going to talk about selected CI and as well what we call the Quest database of accurate excitations energies. I'm going to say a few things about this today. But we also work on couplet cluster here, but mainly for excited states. So we're trying to develop what we call state-specific couplet cluster methods. Okay. We work a little bit in terms of mathematics on, let's say, analytic continuations of electronic structure methods and what happens when you go into the complex plane, depending on the variables that you look at and so on. We work as well on many body perturbation theory, so based on Green's function. So that's approximation that comes from condensed matter and nuclear physics, that basically are very elegant because they kind of resum different types of what we call diagrams. And sometimes you have some very, very impressive results for very cheap. And also we work on density functional theory. And again, trying to develop like state-specific density functional approximations based on small systems and so on. Okay. So if you are a student or postdoc and you'd like to work on this, please contact me and we can chat about it. All right, so I said that I would define the terms in the title. So let me talk a little bit about, you can't see the title, but it's written configuration interaction, CI, because maybe you don't know about CI, and that's okay, because there is many things to know in the world. Configuration interaction is basically one of the oldest and perhaps the easiest method to understand, not to code, but to understand at least. It's very important. And basically what you're going to do in configuration interaction, you're going to try to improve a reference wave function, which is usually the R3-Fock, an R3-Fock reference, okay, by including excited determinants that we call the singly excited, doubly excited, triply excited, and quadruply excited, and so on, until you basically run out of memory in your computer or a CPU time, okay? The good thing about CI is that if you build a CI matrix and you diagonalize it, basically you have the variational principle that tells you that you're never going to go below the exact energy within a given basis set, which is always useful, okay? All right, so basically what it is like, so the sticks, the lines here are molecular orbitals. The arrows are electrons. So basically here you have a good old R3-Fock ground state determinant, and you're basically going to improve your wave function by including singles excitation, double excitations, triple excitation, and so on, okay? So that's going to be basically summarized like this. Okay, so the cool thing about this is that if you start from R3-Fock and you include systematically the singles, give you CIS, the doubles, give you CISD, and so on, you're going to reach slowly but surely what we call the exact solution of the Schrödinger equation, the full CI limit, okay? And that gives you the exact solution of the Schrödinger equation within a given basis set, okay? So that not exactly the exact solution of the Schrödinger equation is within a given basis set. That's very important to understand. For example, if we look at the famous Popol diagram, okay? So here, if I take one basis set, for example, a double zeta basis, and I increase my excitation degrees from R3-Fock to full CI, I'm going to get here, which is the exact solution for this basis set. But if I really want the exact solution of the Schrödinger equation, I have to go to the complete basis set limit, okay? So that's something that we need to keep in mind. So full CI wasn't very useful before because I think Nick Handy and Peter Knowles had a very, very efficient full CI program in the 90s, but we could go to 10 electrons, but it was very, very expensive. But nowadays, so it's become more and more fashionable because we have some new implementation and new algorithm to try to reach this limit. So for example, you may have heard of full CI QMC by the group of Ali Alavi, or the method that I'm going to talk about, CIPSI, today. All right, so why do we care about other method? Is because full CI is very, very expensive. So for example, if you take 10 electrons, okay, which is like the water molecule in 38 spin orbitals, for example, you're going to see if you count the number of determinants that you can create, okay, which is going to basically give you the size of the matrix that you have to diagonalize. It grows exponentially fast, okay, with the number, with the size of the system, which means that you're going to run out of memory pretty fast. So here it's already 500 million, and it's a very, very small system. So we have to find tricks to go beyond this and make it cheaper. Okay, so that's the idea of CIPSI. So here I wanted to show you, like, for example, if I define E as the excitation degree, you can reach the full CI limit by including more and more determinants, okay, singles, doubles, triples, and so on, okay. So that's one way to basically reach the full CI by spanning the entire Hilbert space, okay. But you can use something else that is called the seniority, that is used a lot in nuclear physics. So that's the number of unpaired electrons in your determinants. So if I add step by step the determinant with no unpaired electrons, seniority 0, and I unpair 2, 4, and so on, you can also reach the full CI limit. That's called the seniority. So that's a seniority 0 determinant. There is no unpaired electron. Seniority 2 and 4 and so on. I'm going to reach as well the full CI limit. Okay. I can do a map with the excitation degree and the seniority, and you can see that CIS is going to fill this map from top to bottom, if you want, and the seniority is going to fill this map from left to right, if you want. Okay. The problem with seniority is that at each seniority, you have excitation determinant with all excitation degree. Okay, so it's exponentially expensive at each step, which is quite annoying. So you can combine those two. You can say, yeah, well, I'd like to have low excitation and some seniority. So for example, that's what we've done with one of my postdocs, Fabrice Kosowski. So we defined the hierarchy parameter, which is just a very simple combination of those two parameters, where we're going to fill the map now, but in diagonal, following the diagonal. Okay, so just to keep the cool polynomial scaling of excitation-based CI, that take seniority, high seniority determinants that are more important when you have strong correlation. So it's a way of having a better balance between weak and strong correlation when you want to do dissociation of diatomics and so on. Okay. All right. So you have those different maps. That's what we've done with Fabrice, who's a postdoc in the group. So another way of doing things, and that's the way I'm going to focus on today, is using selected CI. So selected CI is going to tell you, well, basically the main idea is to say, basically there is a huge number of determinants in the Hilbert space, but when you look at them one by one, you quickly realize that most of them do not contribute much to the energy, or they do not contribute at all. So if someone does not contribute too much, you say, well, maybe you're going to leave on the side and we're going to take the other guys in, okay? So that's the idea. So we're going to do a sparse exploration of the Hilbert space, okay? Because the Hilbert space is huge, but most of the space is 0. So let's try to be a bit more clever. So CIPSI is based on this. It's an iterative method that's going to explore sparsely the Hilbert space. So it's been developed in Toulouse by mainly Jean-Paul Malerieux, that you probably know very well. in the 70s, sorry, and he can be traced back to other methods in the 60s by Ernest Davidson and so on. And recently, in the like 10 years ago, it's been a bit like resurrected by people from Toulouse as well. It's completely like out of luck by basically Anthony Semama, who's one of my colleagues, and Michel Carré, who are two close colleagues. And maybe you know also Emmanuel Giner, who is in Paris now. And basically, the same idea developed in different types of methods. Maybe you've heard about the heat bath CI method of Cyrus Umregar. It's basically the same idea. The way you explore the full CI, the Hilbert space, is not quite the same, but it's very, very similar. Adaptive sampling CI from Francesco Evangelista is very similar to this. I actually think it's exactly the same. You have iterative CI, incremental CI, and also full CI QMC, which is just a stochastic version of CIPSI, actually. So it's basically the same. And the cherry on the cake, there is a connection between CIPSI and Barcelona. So I've done my homework before coming, and I think that all those people are still working in Barcelona, and they are all full professors, I think, which means that it's probably a good thing to work on CIPSI. Okay, so I don't know if any one of you are in the room right now, but I found this very nice paper from '86 working on CIPSI. There is a second one 2 years later, and there is a third one. So it was very active in the 90s. Okay, I think it was on what they were calling free class CIPSI or something like this. Very old paper, but very nice. So basically here, just to have an illustration, and that's basically the number of, I think, is the number of determinants that they could consider in what we call the reference space, the variational space. So hundreds of thousands, which is pretty impressive for the 90s, actually. You'll see that now, of course, the computers are much better, so we can handle more than this. But already we could do some very interesting stuff many years ago. Okay, so let me show you like how CIPSI work. So basically here, that's what I call Hilbert space onion. Okay, so it's all my my onion like this. And CIPSI is going to start with a reference determinant, which is usually the R-trifog, but it can be something else. It can be a determinant made of natural orbitals, of localized orbitals, of optimized orbitals, anything you like, okay? And basically, you're going to explore the onion, okay? Starting from the center, of course. So you're going to actually look around. You're going to look at all the single and double excitations that you're going to do from this determinant, okay? And you're going to look at the contribution to the second order energy in terms of perturbation. And if they contribute a lot to this energy, you're going to say, hey, you guys come with me because you look like you're important, okay? So you're going to span one layer of the onion, and you're going to do this again. You're going to say, okay, now I've got 4 guys, and we're going to see, and we're going to do all the singles and doubles starting from all of those guys here, including the center. And we're going to see if those guys on the second layer of my onion are important. And we're going to keep going like this until we run out of memory. Exactly this, okay? And you see that by doing this, you're not going to explore the entire onion because some part of the onion, you're going to throw it away. You always do, of course, okay? And so basically, you're going to have a sparse exploration, iterative, of your Hilbert space. And you're going to try to reach, if you want, the full CI limit like this, okay? So I'm just going to show you a few equations, not too many, just a little bit, just that you understand what happened. So basically, at a given iteration, what we're going to diagonalize the Hamiltonian in what we call the internal space, okay, or the reference space, or the variational space, or the model space, depending on where you're coming from, okay? And the guys which are on the next layers are called the perturbers, okay, and they are part of the external space. Okay, that's what, and you're going to make this variational space grow and grow and grow. Okay, so basically at a given iteration, you have what we call a reference wave function of 0th order wave function, which is just a basic CI wave function, but those determinant I, they can be singles, doubles, triples, whatever they want. Okay, there is no hierarchy in that function. You have a variational energy. You know that this energy is higher than the exact one because that's computed via an expectation value, so that's safe. And what you're going to do, you're going to create your external space by looking at all the singles and double excitations coming from this bunch of determinants here. Okay, and so you're going to look at the contribution to the second order corrections. Okay, and so that number here is for each external determinant. It has a well-defined sign. Okay, so you can grab the ones that contribute the most. Okay, so take the largest delta E and I add them to the internal space. I rediagonalize. I update my psi 0 E0 and I keep going. Okay, so that's super simple. The algorithm is super simple. The implementation is super tricky. Okay, so that's always the same problem with those methods. So the idea is simple, but the implementation, if you do not have a very smart colleague like Anthony Semama, you're probably going to have to do very small system for the rest of your life. Okay. All right, so let me show you an example. So that's the chromium dimer here. So full valence Cas, so it's 28 electrons in 192 orbitals. Okay, so I freeze the core electrons and I say, please do a full CI calculation. It's in quadruple zeta, I think. So here, I'm looking at the number of determinants. Okay, so we can go here to 10 millions and so on and more. And here, that's the energy. So the one that you should look at this moment is this guy here. That's the variational energy. Okay, you can see that the variational energy is always, so basically the full CI limit is somewhere here, is always higher. Okay, and it converges very slowly. So you're going to tell, you should tell me this method is rubbish, and you might be right. Okay, but there's a catch, of course. So what we can do, we need an indicator to know how far we are from the full CI limit. And this indicator is actually very natural in that case, is that we look at the second order energy. So the guy that we haven't taken with us, okay, the rest of the group, we're going to sum all the energies and look at the second order energy that remain. The cool thing about that number is that you know that when this number is equal to 0, it means that you have reached the full CI limit. Okay, it is always negative, and so it's basically going to decay slowly until you reach 0, and you know for sure that you are at the full CI limit. So that's the cool thing about it. So the less cool thing about it is that the sum of the alpha is huge. It's billions of billions and trillions of determinants, and most of them again are 0 or very tiny. So basically what we've done is that we've designed a semi-stochastic algorithm, which means we compute the largest part like deterministically, and the rest is computed by Monte Carlo, if you want, quantum Monte Carlo, okay? Because there is lots of zeros and so on. So, and basically what we do is that we're going to extrapolate our variational energy so that the second order energy is equal to 0. So how does it work? So you remember that's the same example as before, okay? Number of determinants as a function, energy as a function of number of determinants. Here is my variational energy, okay? And here, for example, it's the variational energy plus the second order energy. So you see that it converges much faster, okay? So here it's just a renormalized version, don't worry about it. But what is interesting is that for large wave function, you can plot the second order energy as a function of the 0th order one. And you can basically linearly extrapolate the energy so that you get E2 equals 0. And that value here, it's guaranteed to be the full CI limit. Okay. So in practice, we always do that. Okay. So we basically compute large wave function, try to get in this linear regime to have a very safe extrapolation. And we're going to plot the second order energy as a function of the zeroth order energy as a function of the second order. And we extrapolate to E2 equals 0. And that's our full CI estimate. Okay. So that's how we do it. For example, another example that might be useful, this is a very nice paper by Janus Eriksson that has been done a few years ago, where they basically, so that was an idea by Jürgen Gauss, I think. They basically invited lots of groups, mostly in the US and in Germany, I think. And they say like, okay, we're going to do a blind test. I give you a molecule, that's the benzene molecule. We have a given basis set, CC-PhDs, not very big. And basically, we're going to give you guys the geometry and basically do the calculation, send us back the number, and we're going to compare, blind test, the result of all those methods. So you have some very, very fancy methods. You have like full CI QMC here, which was an old numbers. You have DMRG by the group of Garnett-Chan. You have like CAD full CI QMC, which is a full CI QMC with a bit of couplet cluster. That's by the group of Piotr Pikush in Michigan State, I think, University. You have like iterative CI by Liu's group. You have semi-stochastic heat-bath CI by the group of Cyrus Omriga and Sandeep Sharma. You have the adapted sampling CI and so on. So, and basically what they found is that you have a correlation energy. So that's for the ground state that is roughly around 863 milliarchy. But it's hard to give a better number than this. It's basically within 1 milliarchy. Okay, so we were not invited to the party, but we can still do the calculation afterwards. It's not blind test at all because we knew actually the number. And so we did exactly the same with CIPSI to see what happened. So here again, that's the variational energy, okay? I have my variational plus PT2, and as usual, what I'm going to do, I'm going to plot my correlation energy, which is variational, as a function of my second order energy, okay? Try to push as much as possible so that I get to this nice linear regime, and I can extrapolate the results, okay? So here we went to 200 million determinants, so we had to push very, very far the calculation. And so basically that's the numbers from the previous results, and you see that the CIPSI numbers is here. So that's a different algorithm to get to the full CI limit, but basically you get the same result, okay? And we got basically the same result as all those guys, so we're pretty happy about this. We can do slightly better now because now we can also optimize the orbitals while we're doing the calculation. Okay, so basically for each variational energy, we say, can you please optimize the orbitals so that you give me the lowest energy for this set of determinant? And now we can do that thanks to the work of Yann Damour, who's a third-year PhD student now in the group. And you see that the cool thing about this is that it actually compresses the wave function a lot, okay? So for example, if you take this line for a given energy, here, for example, you have the convergence of the variational energy for R3 orbitals, which is pretty, that's the same rate, but you converge faster with those ones. Here you have the natural orbitals, and basically you have a factor 10 when you go to localized orbitals, and you even have, again, a factor 10 when you go to optimize orbitals. So basically you compress the information as much as possible. So that was very nice. He's done an amazing job for that. Very, very good student. Michel Caffarel, that some of you might know, has used CIPSI to do a calculation in solids as well now. So they have a paper on diamond where they use CIPSI to have a very accurate trial wave function, and they do diffusion Monte Carlo on top of that. Okay, and so they can get, I think that's they do diamond atomization energy or something like that. So everything is into what we call quantum package, which has been developed by Anthony Semana, who's my colleague in Toulouse. So it's on GitHub. It's free. You can download it, use it. It's not very hard to use at all. Actually, CIPSI is very easy. There is no subtle things to parameterize or so on. You just run the calculation and you see how it converges. So it's if you want to have a try, please be my guest. It's normally installed on Linux machine pretty easily. And so basically now what we've done with this amazing program, we basically went to excited state. I don't know how much time I have left. Sorry. 10 minutes? Okay, perfect. Let's finish. So it's thanks to Denis Jacquemin and Martial Bojo-Pasqua, my colleague in Toulouse, is also part of this project. So Denis went to me and said, like, we should design a database of excited states energies based on CIPSI so that we have the exact number within a given basis for some small molecules, and so we can compare other methods. So why we wanted to do this? Well, so we talked about all those TP, SSH, and whatever functional. We like to make fun of DFT people because it's a soup of functionals and so on. And you're probably right. But if I go to excited state methods, it's not much better. Okay. All those methods are excited state methods. At least all those functional are based on the same formalism. Okay. You can implement them pretty easily. Those guys, I'm not sure. Okay. So we shouldn't make fun too much about DFT. And we should realize that also in electronic structure, like wave function methods, we have a big problems with acronyms as well. Okay, so the idea was, okay, let's get some hardcore reference numbers so that we can really compare those methods and know when CASPTT works and CC3 works and TDDFT works and so on. Okay, so that was the idea. So how do you do a CIPSI calculation for excited states? Well, basically, what you do is diagonalize a matrix. So instead of only asking for one state, you ask for 2 states or 3 states or whatever you want. Okay, so that in terms of technicalities, it's not much different. So what is important is that when you select determinant, you select them for all the states at the same time. So you need to have a consistency in your calculation. You cannot select state for the ground state and select determinants for the excited state. It's not going to be consistent. And what is important is that we want to converge the energy difference. Okay, we don't really want to converge the total energy, but we want to converge the energy differences because that's what is important. Okay, so we need to do a selection that I would call state average, if you want, in a CASSCF language. Okay, so that's what we do. And basically, the type of conversion that you have for the ground state is basically the same for the excited state. So there is nothing very different. Okay, and we extrapolate as well. So here, I don't want to show you the numbers, but what I wanted to show you here is that the energy difference converges much faster than the total energies. Okay, and that makes sense. Okay, but you don't have to look at those numbers. Okay, so the first paper that we did, we basically used full CI, so CIPSI to get the full CI estimates. Okay, and so the idea was to make sure that we were completely consistent in our numbers. So basically, Denis did lots of couplet cluster calculation. He went to EOM, CCS, DTQ. Okay, I did all the CI calculation. We tried to use basis set as large as possible so that we could try to get the exact solution of the Schrödinger equation. So the nice thing about this is that really we could see that by using selected CI or couplet cluster methods, we really converge to the same numbers, which is always good. Okay, so we did like 110 vertical excitation energy with oscillator strength and so on. It was like small molecules. So what I mean by this is 1 to 3 non-hydrogen atoms. For CIPSI, it's already pretty hard to converge. Based on CC3 geometries, mostly singly excited states. And we basically define what we call theoretical best estimates, TBE. In basically, usually we use OGCC PVTZ. That's our basis, reference basis. Okay, it has diffuse functions, so the Rydberg states are well described. It's a triple zeta, so the valence state are well described. So everyone is more or less happy. Okay, so that was the idea. And we could actually benchmark popular excited state methods with those numbers. So for example, if you want to benchmark the couplet cluster methods or ADC3, for example, you can really gauge what is the quality of those methods and what is the typical error that you get, okay? So you could see that when you go to CCSDTQ, basically you have basically no error. We could see that CC3 usually, if it's a singly excited state, it's a very, very good method, okay? It's not as expensive as CCSDT and it gives you something very good. We basically found that ADC3 is not much of an improvement compared to ADC2, which is a bit of a bummer because it's more expensive. Okay, so we could really see that those kind of trends in the methods. So the second paper that we did, we went to more challenging excited states that are called doubly excited states, where basically you excite not only one electron, but two electrons. So those guys are known to be very, very hard for couplet cluster, equation of motion couplet cluster methods, because you have to go at least to the triple excitation to get something relevant. So we did a paper with Martial as well on this. And Denis, so Martial started doing like lots of CAS-PT2 and NEF-PT2 calculation to try to gauge those methods for the different singly excited state and doubly excited states. We did some more afterwards, so that's not very important. But for example, that's some result from Martial on that large set of excited states. So we started looking at CAS-PT2 with IPEA shift or no IPEA shift, okay, in the Hamiltonian, looking at the difference with NEF-PT2 with strongly contracted or partially contracted. So that, and you could see that really like the IPEA shift really reduce the error compared to when you have no IPEA shift. So that's stuff that we could see. For example, NEF-PT2, very small difference between strongly contracted and partially contracted, and you don't need the IPEA shift. Okay, so we could really see that. And we could like compare that with other type of single reference methods. Okay. So everything we've put all the data in a website. So it's been done by Michael Very, who was a PhD student with me a few years ago. So if you want to have a look at it and you want to grab some numbers for different type of methods, different molecules, different type of excited states, he's done lots of tools to actually make that easy. Okay. And so it's been used a lot recently by many groups around the world. So there is the group of Martin and Gordon that use it to gauge like orbital optimized DFT for double excitations, or even TDD. He's done a huge TDDFT benchmark on that. There is a Martin Kopp who's done like an assessment of hybrid functional, Calais group and Gures group. They tested the double hybrids on that set of excitations. There is the group of Don Trula and Laura Garigliardi that have done like pair DFT as well a lot. There is a new paper about this. And Rod Bartlett's group has been using it to improve equation of motion couplet cluster, especially for doubly excited states, and also Noskamans and Anthony Semana and Claudia Filippi for QMC, okay, to go to excited states, and a team for DFT. I think I'm going to stop here. I'd like to thank my group and my students and my colleagues as well, and the ERC for the money. Thank you very much.
Thank you very much for this nice presentation. And if somebody has a question, we have some.
I guess if you're a chemist, you're very interested in gradients and second derivatives.
Yes.
And the computation of those is always plagued.
Yes.
Methods like this. Have you broken the back of that?
Not us, but some people did. Sandeep Sharma in Colorado has done as gradients for IDBAF CI.
So you don't get discontinuities and so on if you're looking at a reaction.
Yes, so you have to be super careful about this. So basically, they worked on that many years ago, and but the thing is like the larger your wave function, the smaller the discontinuity. So you really have to push to have something smooth. Yes, yes, exactly.
You made me rejuvenate talking about CIPSI. Thanks. No, and I also like it very much because you presented something very complex, made very simple. So congratulations for the presentation. I have just one question. I'm wondering about the size consistency of the method.
Well, so selected CI, if you don't extrapolate to the full CI limit, is not size consistent. So that's why we never not extrapolate, because otherwise you have trouble. So at the start, Anthony Semama and Michel Cafael designed this version of CIPSI at least to use those wave functions as trial wave function in quantum Monte Carlo. And even by doing on top quantum Monte Carlo, they had some problems of size consistency, because when you go to 10,000 or 100,000 determinants and you do dissociation and so on, you have problems as well. And for example, it's very, very true here, because usually the atoms are super nicely converged, but like the molecules are definitely not. So you still have problems. So for example, that's why in my group, for example, we never, so if we cannot extrapolate to the full CI limit, it's not very useful.
Thank you very much, Pierre-Francois, for the very nice talk. I'm wondering about the implementation of this method in quantum computing.
Yeah. Well, I'd say that at least we can do the same size of system than them. So that is good. No, I don't think people have tried this. But yeah, so it's okay, because you put noise on noise, more noise with more noise. So usually it compensates and kill each other. So no, I don't know about this. Yeah.
Any other questions? If not, let me thank again Pierre and all the speakers of the session and the morning. And Eliseo is gonna continue with the closing.
Well, this is with this session, we finish this journey of the institute. Thank you everybody for coming. But you remember now we have a lunch here together. And at, I think, 3:10 we can start. The new symposium will be the virtual reality applied to chemistry. We will have a very interesting talk. The first speaker is David Glowacki, that he will explain how to use virtual reality to analyze calculations, molecular dynamics. And this afternoon, we will have also a couple of presentations, online presentations from San Diego, people that develop a NanoMe program that probably many of you know, that we have also, I think, 8 or 9 headsets in the institute with this program installed. And then we have already did some sessions for the people of the institute, that it is really an amazing program. And we will have today the opportunity to talk with the people that they have implemented this program for the headsets. And it's really a very nice application. Tomorrow we will follow with more presentations of virtual reality, but well, I will introduce them later. Then thank you very much. It was really a pleasure. I think it was really nice. And now we'll have the lunch together. Thank you.